Howdy everyone and welcome back. And we've been talking about electric fields, we've been talking about magnetic fields, and we may step back and think, why have we been talking about this? Now, I like to think about there's been some interesting applications and everyday objects that have been able to actually exploit these things to build and to use. But there's also another really interesting purpose to learning all that. It turns out electric and magnetic fields aren't really separate concepts but are interlinked. And today is essentially going to be the culmination of that. And essentially from here on out, we're just going to learn about the applications of the combination of the two. So it turns out light is the combination of the two, and we call it electromagnetic radiation. So essentially the story is a guy named Maxwell took all the equations we've been working with, he's, Ampere's law, Gauss's law, Faraday's law, and one other one that doesn't have a name, but essentially identical to Gauss's law, but for magnetic fields. But he wrote them all down, put them all next to each other, and figured out if he added them in some type of combination, he would actually get back a wave equation. Now, a wave equation is a type of differential equation that you can write to describe things like waves, like you have a piece of string and you have a wave moving through it, or you have water and you have a wave moving through it. Both of them, essentially, you can go write down a similar equation that governs how it moves at essentially the surface of the water, or how the bump in the string moves. But you can do the same thing with electric and magnetic fields. And a lot of, that seemed like a crazy idea, but that's essentially how we describe light. It's the combination of electric and magnetic fields, or sometimes we use the word photons, but it's also a wave. It's a particle and a wave. And also what came about during that is that when you write down a wave equation, it has a speed, and for light, it was just a number. And so Maxwell maybe thought that was interesting, but then Einstein later came and said, hey, that's interesting. Light is just a number, meaning it doesn't change, it doesn't depend on the frame you're using, and then you get crazy things like special relativity and general relativity later. But essentially, we've come and take electric fields, magnetic fields, and realize they're interrelated. And maybe we sort of noticed that with Faraday's law, when we noticed that changing magnetic fields creates electric fields, and turns out, the other way is backwards. So essentially, if you change one, you can create the other. Okay, so what do I mean? So sometimes we write this sort of representation of light. You have an electric field being created and a magnetic field being created, and they're both changing, and they're essentially both creating one another, governed by Maxwell's equations. And this is sort of one way to think about light. It's you have a photon, and it has to have electric and magnetic fields associated with it. And there's a few other equations that we can use there regards to light. First off, the speed of the light, and this is really true of any wave, anything that has a wave equation, is its wavelength times its frequency. And this is just a fixed number, the speed of light, about 3 times 10 to the 8 meters per second. Also, if you're interested in the energy of light, so light, there's some weird properties. Light doesn't have mass, it's massless, but it does have energy, which may be something that we're not used to and it's hard to think about. But because it has energy, it also is going to have momentum, and it's also going to have pressure. It's going to be able to create pressure and exert forces on things. And this is sort of where we have to step back, and we have to realize a lot of the physics, a lot of the math we've been working with is from this classical Newtonian perspective. But we essentially been moving through the 1700s of math with classical mechanics. We've been talking about essentially 1800s math with electrodynamics, and now we're starting to move into 1900s, where people have figured out something we call new physics, where you have things that don't have mass but can still exert forces. So it turns out there's some things that are a bit more fundamental than what we've been talking about, but it gets really complicated. So it's like when you teach physics, you teach about the most basic things, and how we learned it first. Okay, you got that. Okay, then let's add on what's a little bit closer to truth but a lot more complex, and especially more mathematically complicated. Okay, we do that. Okay, but what's really true? And then you keep building up until you get closer and closer to the truth. It's almost like you're not ready to hear it all from the beginning, because it'd essentially be overwhelming. But light has a lot of other interesting properties. So maybe we've seen a plot like this before. So when we mean by light, it's not just visible light, but there's a lot of other different types of light that especially we use in our everyday life and end up being important. You have things that are very low frequency but high wavelength, and something that are very high frequency but low wavelength. So you have things down here, radio waves, microwaves, down to infrared, visible light, that's the light we're used to seeing, up to ultraviolet, X-ray, and then gamma ray. So what does this mean? Well, go from low to high energy. So radio waves are really low energy. Radio and microwave is usually what you use for communicating. So they're very low energy. It doesn't take very much for a phone to create a radio wave. It doesn't take too much battery. And the other nice thing about it is because it's low energy, it tends radio waves to move through things. So you're able to use a phone while being completely inside. But even those walls can block visible light. Because if you have a wall, you can't see through it. But radio waves can pass easily through it. You can still use your phone in a completely encapsulated space. Although once you have enough stuff, it becomes harder and harder. So these end up being very useful. Then we go up to microwaves, and we know one application of microwaves. It's actually a very specific frequency of lights that microwaves create that essentially goes and excites water and gives it a lot of energy. But other than that, microwaves is generally still pretty low energy. Then you have infrared. If you have something that you heat up, like a fire or a old incandescent light bulb, most of the energy it's putting off is infrared, and you can feel that as heat. And you have visible light, and hopefully we're used to that. And then you start getting to the higher energy lights. So all this stuff down here is pretty harmless. It's very low energy, but once we get to a certain part of the UV scale, light becomes more dangerous in terms that it has enough energy itself to start causing skin damage. It's just individual photon now has the ability to cause these reactions in your body, and that's why we generally consider them dangerous. But luckily, these, just like how radio waves interact very readily with, I said backwards. Radio waves don't interact with things very easily. These ones do. So you can block most of these with a piece of paper, or we have an atmosphere that blocks most of these, although part of the UV still kind of gets us a bit. But most of this is still blocked by our atmosphere. We don't have to worry too much about it unless you had things that are radioactive. Radioactive things throw off a lot of this stuff. This is dangerous ionizing radiation. We've got to be careful. Okay, just to keep it, it's a good thing to keep back in your mind, learning about things, learning about people saying that this or this is not dangerous. Good thing to keep in back of your mind is what type of light are they talking about? What does it generally do? Okay, another thing we might be interested in is light from the sun. So it turns out most of the energy of the Earth is being we get it from inevitably the energy of the sun. Most animals, survive off of plants, or survive off all the rest of the animals eat those animals that eat those plants, and the plants get the energy from the sun. So that's generally how it goes. So it might be interesting to learn about that. Okay, so a few terms that we might use with regards to looking at the light from the sun is intensity. So that's going to be the power per area. So that's something that's a constant for the sun at our distance. And then if we just want to figure out how much power is being delivered, say to like a solar panel, we could just multiply by the area by that constant. Another thing is that the sun exerts pressure on us and exerts pressure on the Earth, and it's not very big. But when people talk about opening up a solar sail and be able to fly across the cosmos, they're talking about the pressure that the photons, again, they're massless, but they do have energy. They can exert a pressure. They talk about that sort of pressure. Turns out it's not very large, but it's something that if you have a satellite, you should be wary of it, especially one that's very sensitive in its position, that you may have to counteract the pressure caused by the sun. Okay, so let's do some problems, and these aren't going to be crazy. It's more, it's more of a conceptual sort of chapter, more conceptual stuff to get down. I don't think the math's too crazy here, what we're going to be demanded. But let's start with, let's just do two problems with the light from the sun hitting the Earth. So the distance, the average distance, because it does oscillate a little bit, between the sun and the Earth is about 150 times 10 to the 9 meters, so 150 billion meters. The speed of light is fixed. It's just a number, roughly 3 times 10 to the 8 meters per second. We might be interested, how long does it take for the light to get from the sun to the Earth? Now, light is extremely fast. This is very fast. In fact, this is the fastest anything could be. It turns out, we learn from relativity that when you start approaching the speed of light, weird stuff starts happening, and it's really this universal speed limit that, as far as we understand right now, as far as we still understand, we can't go faster. We can't make a particle go faster than that. So this ends up being this speed limit, and therefore light is going to have a time delay from going one place to another. Now, if we're in our everyday life, we have light, coming from our lamp to our eyes. It's pretty much instantaneous because this distance is really small, and this time ends up being not perceptible. But here, this is a pretty big distance. So, what does the time delay look like? Remember that if looking at an average velocity, it's going to be the distance over the time. So we can just solve for the time here. We multiply the t, the other side, divided by the c. We get d over c. So we get this, distance that we're given in, and then we put in the speed of light here. And we learn that it's a delay time of about 500 seconds, which is about, on average, 8 minutes. So it's saying that if the sun just went out, it just stopped working, went completely dark, we wouldn't know about it for at least 8 minutes. And there's, as far as we understand right now, and this again really the limits of our physics, people want to push this and figure out, is that really the speed limit? As far really as we understand, that's actually the soonest we could learn about it. There's no way we could put a little probe near the sun and tell us faster, because that probe would have to also emit a light signal, which would go just as fast as the sun going out, the remaining light from the sun still being emanated out. So 8 minutes. Okay, let's do another problem. So we might be interested in the pressure that the sun is exerting on the earth. So there's a couple things to keep in mind. So we have an atmosphere. So some of the light comes in and some of it gets reflected out. This is just generally true if you have almost any substance that isn't perfectly dark. You have a certain amount of that's going to get absorbed, a certain amount that's going to get reflected or dissipated in some way. Well, you know that everything in this room isn't perfectly absorbing the light because you can actually see it. So some of the light's hitting it, coming off, going into our eyes. So not going to be perfectly absorbent or perfectly reflected. It's not a mirror. So some combination of the two. So learn that the pressure, and this is going to be pressure, not power, is going to be the intensity of the light divided by the speed of light. So if we wanted to get the total pressure exerted on, and this is not the force, this is the pressure. So if we wanted to get, actually a force, we would be concerned about the cross-sectional area or something like that. But to get the pressure, we have to use both the light that's getting knocked off and the light that's going straight in. So it turns out the light that's getting knocked off is going to actually exert twice the pressure as that being absorbed. And you can think about it in a few different ways. Call that momentum is conserved with these sort of interactions. So if the momentum is conserved, I come in here with this amount of momentum, and then leaving with the same amount of momentum, go in the opposite way, I would have to have gained double that going this way, as opposed to I come in with this amount of momentum, okay, then we're stuck together, we still leave with the same amount of momentum. It's a little bit weird to think about, but if you throw a tennis ball against the wall, bounces off, it's going to exert a larger force than just a thing of putty that comes and splats against the wall, because it need to have pressed off to it in order to have changed direction. That's sort of the thing. So we have to keep both of these terms, and going to have to pay attention to both of them. So the total pressure is going to be the absorptive pressure, the pressure from things getting absorbed in here, and the pressure from the things getting knocked away. So learn about 62% of light comes in and gets absorbed, 38% gets knocked away. So that's going to be these two numbers. Remember, it's I over C, and the amount that is getting reflected off, it's going to count for double. So if we add that up, find it's 6.3 times 10 to the negative 6 newtons per meter squared, or pascals. Now, is that a lot? No, that's not really a lot. So the atmospheric pressure is something around 10 to the 5 newtons per meter squared. So it's very much a few orders of magnitude, 10 or 11, below this. So when you're outside, you're not feeling a lot of pressure being exerted by the sun, especially compared by the air around you. It's much more significant. So this is not something we likely will feel or notice too much in our everyday life. And I don't think we generally do. We don't really open up these giant sails and be able to catch all that solar wind and be able to blow ourselves around. No, it turns out the wind is much more important for blowing us around, and atmospheric pressure and things with mass end up counting a lot more in terms of everyday life. So that's just a little minor sampling of some things with light. I think we're going to keep talking about it in another video, but as far as for now, I think that's a decent start. Okay, thank you as always for watching. Really appreciate it. Thanks for all the support. I just think things are going well, and really, I have a lot of ideas what I still want to do with this channel and sort of videos I want to make. And I think after teaching this course, I think I will start trying out some things. But anyway, thanks for joining me. Appreciate it. I'll see you next time. Bye.